Okay, this is going to be the last recording on shear. There are a couple of examples I just want to show you. They're not really different. What it is that the calculation of VU may not be as clear as in the other cases. So far we've been doing everything with VU at the distance D, right? And those are cases like the ones shown here, right? So you calculate your value at the distance D, you have a column and a beam, you can do that at the distance D. You have a beam framing to another beam. As long as you have compression reactions, right? Compression reactions, then you can find your shear at the distance D. And it's conservative. I mean, it's good to do that. It's still conservative, even though you're doing at the distance D, not at the face. And also from the point of view of economy, right? It helps you reduce, the number of stirrups you're going to put in there, as they are not needed in these cases because of the way the crack develops. You don't need to worry about the shear on this location. It's the shear at D where you have to start worrying about it. However, we learn there are other cases, like this one, for example, when you have a tension reaction where your shear should be taken at the face of the member. You're looking at the interior design of a connection, then you have to take it at the face. You have an axial load or a point load, right, within the distance D, then you have to do it at the face. If you load your beam at the bottom, below the neutral axis, then you also have to take it at the face. Okay? And so these are the cases that we worry about it. They're also shown in your code, so you need to find them. They are in your code, of course, in the section for beams, right? So these are the section for beams, chapter 9, right? And here they are. See, this is the one where you load below the neutral axis. Your critical section is at the face of the support, right? You have a tension reaction, face of the support. You have a point load between the distance D, you take at the face of the support. Other cases at the distance D. Okay? So that's one of the examples I want to do, and so let me look for it and do it. Let's see. Okay, so we went past all that. Okay, let me see, what is it? So we done that, we have done several of these already. So they're all very similar. I mean, you had to find your VU, then you find your value at the distance D. I show you the cases where you had to consider your bearing added to your D because things are taken from the face of the support. And normally we model things like this. We don't show the actual bearing width, right? So we put these little symbols to show our supports, but they're bearing areas, right? And the code says to take it from the face of the support, which is the face of the bearing. So you have to add that width of the bearing, or half of the width of the bearing in most cases, right? So we've done some of that already. But let me see, what is this one? No, that's very similar to what we already done. And the point load, we done that with the point load on the cantilever. The important thing about cantilever, don't forget, is that when you find your number of stirrups and you do your spacing, you don't want to go past the length of the cantilever, right? Because you will be putting your stirrups in the air. You also don't want to put it right at the end of the cantilever because then there is no cover distance to protect that stirrup. So you had to finish that at least 2 inches before the end. I mean, something like that. You can do 2 inches, 3 inches, 4 inches, but about that, you had to cover, you had to protect that stirrup at the end. Okay? So you don't have to go all the way to the face of the cantilever. So this is a wide beam, and here is the one, okay? So you have here a simply supported inverted T-beam. So it's an inverted T-beam, right? And the load is being placed right on this side, right? So that's how it's being loaded. And of course, the load is on the bottom section of the beam, all right? So this is a case where you have to take everything at the face of the support. There is no distance D here to calculate, okay? And so the length of the member is given. The values of the loads are given. We're using number 3 stirrups. Ignore any torsional effects. Okay? And that's simply because what happens if this is a live load, what happens if you load one side and not the other side, right? And you can have that torsion. Assume a D value of 35.5. They give you the F prime C and the Fy. So we find our beam weight, and as always is the area of the cross section, okay, which in this case is a T shape, times the gamma. And so here is the area times the gamma, right? We change it to feet, and so we got the weight in kips per foot, right? And so that will be a dead load, right? So we have now the weighted beam, and that's all we have here. There is no uniform live load given, okay? So we don't have that, but we do have the weight of the beam. And we do have these PDs and PLs. So because of that, we have to use 1.2 and 1.6, which means that here we have to do the same, okay? But in this case, that's 0. The important thing is the 1.2. So we got the uniform load and we got the point loads. Okay? And in all cases, you are having 2 PUs and then your uniform load, right? And so you do your analysis and you get your reaction here and do your shear diagram, right? So it's going down a little bit, then it drops because of the PUs, then it continues down, uniform load, then it drops again, and so on, right? So the reaction is equal to WUL over 2, right? And there will be 4 PUs on each side, right? So 4 PUs on each side. So that's your reaction, right? Since the beam is loaded at the bottom of the beam, right? Then you are going to take the shear at VU. So right there where you are at the reaction, we're going to do it there and not a distance D. Now, if they give us a bearing width, right? Sometimes I give you a bearing width. In this case, I didn't, so you don't know what it is. You're going to do anything about it. But if you have a bearing width, then you could move your shear to the face of the support. And so that would be 6 inches or so, right? And so typical, I mean, the minimum usually bearing pad will be like 8 inches. You may have 4 inches then minimum to move to the face of the support. Okay? But basically you're doing your shear right where you find it in this case. There is no distance D to calculate here to find your shear. So you will use that maximum value. So we find our V sub C as always, right? And so there is no difference there. You've been doing this already. Then we find this quantity, right? As I said, for as long as you're using only this equation, this happens to be half, okay? And so it will be half. But be careful, because if you use here the axial load, right, then this is not half anymore, right? You actually have to find it, okay? So since the BU at the face, we're going to assume that that's right at the face, right? Since we were not given a bearing pad, then we will use 221.7. It's a lot bigger than this number, so then we will need to put stirrups, okay? Now, how long do we have to put stirrups? Well, We are looking for 30.3. And so you look at that, 30.3 happens right here, right? So there is no need to do any proportions, anything. I mean, you know that 30.3 is there. That's the location of the second set of PUs, right? So that happens then at 10.5. Okay? So at 10.5, you have the location of the distance that you need to cover with stirrups. All right. The required phi sub s, of course, is the difference between your required shear to cover that you have and your phi sub c, right? So that's 161.1. Most formulas in the code are without the phi factor, so we're going to remove that, and that will give us 214. This number now is bigger than the 4, but is less than the 8, right? So because of that, your S maximums will start with D over 4 and 12. Now D over 4 is 8.9. Normally, I mean, we try to, normally you'll be running, rounding down in most cases, okay? This 8.9, 9 inches, I'll go with 9 inches, okay? But if it's 8.8, round down, okay? So this is the maximum spacing between the face of the support and that. So the VU, right, that we will have, right, between the face of the support and a value that's equal to the maximum, which is this is the 4, right? So here is the limit of the 4. So that's the 4 value. We multiply by the phi factor, then we add the concrete. Then this number right here represents the number where we can stop using this 8.9, because at this moment, right, your shear now, your phi sub s is exactly equal to 4 or less. Okay, so at that moment, then from there all the way to, and this is wrong, okay, I need to change that. So that one, let's change it. So that, remember, is half, but it's not truly half, because depending on what equation you are using. So this should be, so we need to get used to doing that because of the new code, right? And so we want to put there our lambda, right, which happens to be exactly half in this case, but it is better to have it right. Okay. And so that will be that, and that's the point where we need to cover this. We had the stirrups need to go all the way to that point, right? And so that's all we're saying. So all we're saying is now that as long as you are now between this point and this point, your maximum spacing becomes 17.8, 17 inches basically, right? Now you use here 8 inches is not wrong. I mean, you can try, that's good, okay? You can do 8, that's okay. And then always check minimums, right? Because this one always is in the first column of your table. Remember, in design aids, right? And so, but we want to check minimums, and when we check minimums, we get 14.7 as the minimum spacing. Okay. So in this case, notice that due to these minimum requirements, right? The spacing where stirrups are needed within that area is not going to be 17.8 or 17 inches, it's going to be 14 inches. Okay? So in this case then, as soon as you go below phi sub c, you can use a maximum, but it's limited to 14 inches. 14 inches. Across, because of this, the case that we were between between 4 and 8, right? Then across, your value is d over 2 and 12. D over 2 is 17.8. We have 18 inches on the web, so definitely we are okay. Okay, 2 legs will be within that distance. Okay, so let's summarize what we got here so far. Okay, so here is our graph, right? So from here, right, from this point, right, up to a shear value of 181.9. So let's find that number. That would be someplace around here, right? You have to use a maximum spacing of 8.9. So I said 9, you can use 8. Okay, that's okay. You are not sure, better to round down. Shear, round down. Okay. All right. So from here to here, we got that number. Okay. After that number, we can use the d over 2 on that. So let's go to the, let me see if I had the design aids here. Design aids. Yes, I have design aids. Okay. Okay. So we started here because we were greater than 4, but less than 8, right? So you are using these values, and this one controls, right? And so that takes us from this point to someplace in this line. Okay? Then between this point and, right, the value of phi b sub c, right? And what is that value of phi b sub c? We have a value of phi b sub c here, right, of 60.6, right? So going back here, between that and 60.6, what is that number? That number is going to be someplace here, 60.6. So between here and here, you have to use the spacing control by this maximum. Okay? That's the maximum. After that point, right? After that point, and the minimum, right? Because we found that minimum, now we're controlled by 14. Okay? And so that will be from here all the way here, right? 14. But the problem is here, right? You found that you have a 17 based on the table, right? Because the table only shows you this, right? And I say, and I always say that, right? Do not forget to check your minimum. Okay? This is your minimum conditions. Okay? So that means you have to have satisfied this minimum at all times. Because remember, your formula says I can use the formula for B sub C as long as you provide AV minimum. Now, we are not finding an actual area, which you could, right? But we're using the spacing, so we need to satisfy the spacing. So these formulas are these formulas for AV minimum. So this is the spacing corresponding to AV minimum. Since this value is giving you a 14 versus a 17 here, you have to use 14 from here all the way to where your shear becomes equal to the number we just corrected, right? The half, which is the 30.3, right? So all the way to 30.3, you have to use the minimum, right? And so you have to satisfy that requirement. Well, that happens to be here someplace, 30.3. So from here to we're doing minimum spacing of 14. So far we got then the value here of 8 inches or 9, depending what you want to do. There, and then from here to here, controlled by 14. From here to the end, right, it's a very small shear, but unless you want to use the other formula for calculating phi b sub c, you also had to provide a spacing equal to the minimum. So really then from here all the way to the center, you will use, in this case, minimum spacing. Okay? Because minimum spacing controls over the 17 inches that we found here. Okay. All right. Okay, but the formula, remember, in both cases for the 4 and for the 8, right? So when you pass the 4 or the 8, you have to find this value, right? You have to find that value. And so we find the value, and it's 218, so that's 2 inches. Oh, that's very close, right? So then what that means is you're using a stirrup on number 3 was not a good idea. That's all it means. Okay, so if your spacing is too small, you change the size of your stirrup. That's how you decide if you need a number 4 or you need a number 5, right? So depending on what you get here on spacing. So let's change it to 4. So if we change it to 4 now, what happens to the minimum value? Oh, the minimum value changes to 26.7. All right. So now what happens? So if I change to number 4, then the minimum spacing, the corresponding spacing for minimum requirements is 26.7. This value, wait a minute, not that one, this one does not change. It's still d over 2. So now 17 controls. Okay. So if we change to number 4s, right? If we change to number 4s, now what happened? Change with number 4s, we have, here we had to use, you round down, it will be 8 inches. Or you feel comfortable, you do 9, right? And then from here to here, now 17 controls. From here to the center, you only need AV minimum. So that is your 26, right? 26, what is that we found? Yeah, 26.7, so 26 controls, okay? All right, so by using number 4s, we have 8 inches or 9, depending on how you round. Here, we got 17 inches, and then from here to here, I can use 26, okay? That's how things have changed by changing from a number 3 to a number 4. When I use the number 4, I get a spacing of 397. That's pretty close. I said 4. Okay, so I'm going to use 4. You want conservative, you can do 3. This value of 4 is less than the maximum that we found of 8.9, right? And so now we have to start then not with 8 or 9, we have to start with 4. Okay. Okay. Now we need to create a table, right, to know where things happen and we have to change. However, in this case, this table is not needed because the way the graph is, right? Right, because we know that we know the length that we need to cover by stirrups. We already found that. I mean, we know exactly what's at that 10.5 distance, right? So we can simply look at the shear diagram and decide where we can change. So you look at this, right? This diagram. I mean, 221 to 218. There is no difference here in value pretty much, right? So you are going to use a spacing of 4 inches all the way to the first drop. There is no need to do a table. I mean, you're not changing anything here, right? So 4 inches all the way here, right? Then we drop, right? And we get to this 114. But we already said that from here to here, right? We have a maximum already, right? We already determined our maximum of 17, right? Okay, so that means I can use anything equal to 17 or less. Okay, so let's go back here. No. So we did that after the first point, right? Now, when we do this 114.3, right, which is when we drop, you can find again your calculations if you want to know what spacing do you need for this number on. So now your shear becomes 114.3. So that's your VU. My phi sub c hasn't changed, right? Find my V sub s. I found that is below this number, right? We know that already. So it is below that number. And we find a V sub s. Okay. So again, that's 17. We already know this. But we found that we need a spacing of 12 required, okay, based on the S. Okay. Because remember, the 17 is the maximum spacing, but not the required value based on your shear that you have at that location. Okay, so you always have to find that. Okay. So maximum value here was 8 to 9 inches. Maximum value from here to here, 17 inches. Maximum value from here to here, 26 inches, right? So going back here to your design aids, right? What you found is these values. That one, so this one was your 8, 9 inches, right? 8.9, 17, right? And then your 26. So these are your maximum values that you can use. But we haven't checked this one. You always have to check this one, right? When your VU exceeds phi sub c, you have to check this one, because this one will give you, and this is the space that you need based on your VU. Okay? These are the maximum, but this is what is required. Okay? So let's see. And that's why it makes it confusing here, because they say required spacing, but this required spacing refers to this one, okay? Mostly, that's required based on your VU. This one is really your minimum, okay? This is your minimum, and minimum is required too, because you cannot exceed that minimum, okay? Otherwise, you cannot use the formulas, all right? So in a way, it's required, but it's not. Really, the required here refers to this. This is your S required. Okay? And these are kind of your maximums depending on where you are. Okay? And so my S required for 114.3, right? So it's like here is like you have a new diagram here. Okay? Like your beam starts here and you have to check what you need. So that's all we're doing. We're rechecking from this point here what happens, right? And so I do that, right? And I found that my spacing is 11 inches now. So I had to use that spacing to start with, right? So 11.9, let's say again 12. So I definitely had a good lawyer here protecting me here, because I'm running up all this right here, right? So 12 inches here, I'm good. It's less than the maximum, so I had to use my 12 inches, all right? Okay. So I go then, and I say 1 and 2. Remember, we start 1 and 2. Then I had to do the 4 inches, right? 10 at 4. Mm-hmm. And let's see, we had these right. So that's 40 and 42. let me see, we have it right, 40 and 42, right? So the first drop is at 3.5, and so that is 36, right? 42, right? So that's exactly 42. So we're good then. So we have covered this portion as required, but a spacing of 4. At this moment I can change to 12 since I rounded up, right? And I can go from 12 all the way through here, right? At this moment, what happens is going to drop to this point, and I don't need really anything except my minimums, right? Okay. And so I have then covered all that distance, right, by doing that. So I got 1 at 2, 10 at 4, and then 7 at 12. That gives me 84 inches additionally, right? 84 inches. And do we have enough? I think we may, yeah. 7 times 12. That happens to be 84, right? So we have covered everything all the way to the second drop. Okay. Then we still have another 3.5 that needs to be taken care of, right? But with that one, we are going to use what? The 3.5 that it remains, we can use minimum spacings, right? And so you can see here that I'm adding, right? Then to satisfy AB minimum, and for construction purposes, add 2 more stirrups at equal spaces through the center of the beam to avoid recalculating a new concrete shear strength using the third formula in the ACI. That's because we got 3.5 feet left. That is 42 inches, right? So we're putting those at 21. You would put 2, and 21 is less than the 26. So we're good. We satisfied AB minimum. Okay. So that's this example right here where we apply the load on the bottom. So the only difference is that you don't use the distance D for your calculations. It also shows you a couple of things, right? It shows you that you need to check, right, your different shears at this location. So this is a 114.3. So I need to check that from here on I have the right spacing. I found the maximum, but don't confuse the maximum with the required. The 114 has a required spacing. The 221.7 has a required spacing. Okay? But there is a maximum here. There is a maximum here. There is a maximum here. Okay? But there is a required spacing. Okay? And so you need to find the required spacing. So in this case, the required spacing control over the maximum. Okay? In this one too, the required spacing control over the maximum. Okay? So you treat this like another beam, like you're starting here now, and you do your analysis for that part. Okay? All right. The next example is also interesting because now we're going to include the effect of the live load, right? As it will give you maximum shears, right? So it's very similar to what we've been doing. So we find our weight, find our loads, right? We load this thing. But we don't get this diagram where it crosses through 0 anymore, right? Why? Because we have learned, right, in the notes, right? We did that. We developed this, and let me go back to that. Wait a minute. Wait a minute. I went past it already. Well, that's okay. Okay, here, right? So here we went through this, right? And we find out that the value that happens here, the maximum, is when you load this way, but you only load with the live load because your dead load is always uniform, right? So then that value at the center depends only on the live load and is equal to your live load times L divided by 8. Okay? that's the value that shear that we want here. So this value here, right, is equal to your factor live load times L divided by 8. And so that's what we're going to use in the calculation. Okay. So we're going to do that one. So we did that one already. Okay, here it is, right? So we got the load, right, right there. I did find my separate live load. Remember, using the same factors, okay? Same factors, because that's your load combination. This is the one that controls, right? So we had to use the same factor. So here is the total value, but then here is the WUL ln over 8. So this is my maximum at the center, 12.1. So now we got a 12.1 here and not a 0 anymore. Okay. Since we're loading at the top and we have a compression reaction, then D will be 17 inches. So here you have to be careful, right? You will say, oh, okay, I want to find my value at the distance D. Okay. So I'm going to subtract my load, right? Times D. That's what we've normally been doing. We can't. We can't do it anymore. Why? Yes, because this diagram now is not the diagram for this case. It's the diagram for this case and the case with having only half of the live load applied on one span. So it's an envelope, okay? So it is an envelope. So then we cannot use this W anymore because this slope does not match this load. Remember, the shear diameter for this load like this, like it is shown here, will go through 0, right? That's a different slope. And so we will get the wrong values. So we have to use the figure. Okay? To use the figure, what I did is simply found an equivalent slope, right? And what is this slope? This slope is nothing else but my equivalent load, right? That's what it is. Mm-hmm. So when I do that, right, to match this slope like this is equivalent to having a load of 4.7. That's what you really have here, right? In there. Mm-hmm. So now so the better way to do this then is simply do that. So the change in shear will be simply the slope times distance. So now we use the slope times distance, right, to get our value. Mm-hmm. So notice then that my load was not the 4.4, is not the 5.8, so I'm going to use any one of those, is 4.7. Okay? So that's my equivalent load, which is simply the slope of the line. So now we're back to geometry here. Okay, you're finding your slope, and then I want to move down in the slope and find the value of the distance D. That's all we're doing. Okay, so we do that. This is now my value at the distance D. After that, process is the same. Okay, we are going to find our phi B sub C, right? So there is the value. Here removing the phi factor in case we needed it. Here is the limit where we need the stirrups, right? Our shear is at the distance D, right? Is 57.1, which is bigger than the limit where we need the stirrups. So we had to put the stirrups all the way to that location. Yeah. And so we're looking at 9.7, right? So where is 9.7 in my graph? Right, so that's 9.7. We know exactly where it happens. It happens someplace in here, right? Because this value is 12.1, so 9.7 is someplace in here. So that means then I need to put the stirrups all the way to the center. I had to cover it all the way to the center. Okay. Mm-hmm. And that's usually the effect of this partial loading for live load for shear, that you had to put the shear stirrups all the way to the center. So some people simply design their stirrups all the way to the center. In that case, you're covered, right, for that all the time. All right, so that covers all the way to the center. Remove the phi factors, right? So I can find my V sub S without a phi factor. So we've been doing that. That's 50.3. Now I compare to my two limits, the 4 and the 8, is below the 4. So I have my D over 2 and 24 as my checks, right? My maximum values. So I had to use 8.5. Okay? But then as the load goes down, because it's still going down, right? Eventually we're going to get these cases. You always check these guys, because remember, these guys represent the minimum requirements, okay? So you need to satisfy that, all right? So 8.5 then controls an 8.5. So you got 8.5 pretty much. So that's your maximum. Okay? My maximum is 8.5. I cannot exceed 8 inches. Okay. Across, well, it has to be 17 inches. We got a width of 12, so that's satisfied, right? So, what is the required spacing? My required spacing now is based on what I have, my shear that I need to cover. Well, that happens to be 4.5. This 4.5 is less than my 8.5, so I had to start with 4. Okay. So I'm going to start with 4, and I just want to change these S's because the code changed all to lowercase values now. So we got lowercase values for the S's. Okay. All right. So I got to start with 4. Okay. So I'm going to do a table between 4 and 8. And of course, I'm going to see how I'm going to change that. I mean, I do 4 and I find my, as we do before, V sub S, right? And then you add, to this one, you add V sub C, and that gives you the shear that you have at 4 inches. The question is where 61.5 happens in your diagram, and we're going to use this formula, reaction minus load times X. But your load, remember, your load is sort of an average load, and is that M, right, the slope. So this is your average load that is causing that diagram, right? The M value, yeah. Right here, right? So that is your equivalent load that is causing this diagram, because it comes from different diagrams, all right? And so we get that 4.7, so we're going to use that instead of a W in the formula, and so we get that one there. So I get my number. Then I say, well, what happens if I do 6? If I do 6 inches, my phi V sub S is 28.1. I add my concrete, and I get that. Now I need to find where this number is. So I put 47.5, I put it here, right? I know my reaction, I know my M, I solve for X, okay? Now be careful that this X, you will get it in feet, and so you have to multiply by 12 to change it to inches, right? Because it's going to be in feet. Then you do 8 inches, do the same, put the 8 inches here, find your phi V sub S, add the concrete strength, you get that one, put this value here, right? Solve for X, and you get your numbers. Okay? So, that means that I could change to 8 inches after 60 inches, right? Otherwise, I cannot do it. So I need to cover 60 inches before I can switch to 8 inches. So that's what this is telling me. So I have to start with 4. So I start here. Let me straighten. Normally we start with 1 and 2, right? So that would be 1 and 2. But I do 1 and 2, and then I got 4 at 14. That would be 58. And below these numbers, I cannot switch to 8 inches. I would have to have 15, right? And 15. So okay. So now I have 15. Okay. So if I do 1 and 2 and 15, right? Then I got 62. Okay. But I need to put, in this case, I need to put one stirrup right in the middle, right? Because that's where I'm stopping. Because left and right and left will be the same. So I want one stirrup right in the middle. Okay. So I got 62 left, right? So we did 1 and 2, and then that's 62, right? And I need to cover this 132, right? And so I need to cover 70. Okay. 70. So the only way I can do that, one way I can do that is change to, instead of using 8 inches, because that's 8 inches, I can use 7, right? 7 will be satisfied because I can change to 8 when I got 60. Then definitely if I'm already past this number, I can use 7. Okay? So I can do 10 at 7, right? And that would give me 132. Here, when I decided to do it was 2 at 2. So, right? 2 and 2 inches, and then 14, 4, and then 9 and 8. And that would put me 1 right in the center too. So always put this one on the left side, or in this case, at the face. You can say, well, I can add the 2 inches here at the end. So I can do 1 and 2, 14 and 4, 9 and 8. Oh, I'm short 2 inches. Oh, let me put 1 and 2. Okay? Yeah, you can say that, but that doesn't look right? Because you are putting now a stirrup at 2 inches where you really don't have a very high shear. Your shear is pretty high here, right? So you want to put those 1 and 2s right in here, rather than at this end, right? And so that's why I did this, okay? This is something new, okay? So that's another way to set up your stirrups. You can do this. 2 at 2, 14 at 4, 9. Okay? Now a cleaner solution would be this one. 1 at 2, 10 at 4, 15 at 6, right? We can do that because 40, here you get 42 inches. You need 42 pretty much to change to 6, so I can change to 6. But we also found 1 and 2, 15 and 4, and we can change to 10 at 7 instead of 8. Now 4 to 7 is not like a nice number, but that's okay. We can do that too. Right? So this example then, what it shows you here also is that the length of stirrup now got all the way to the center. Okay? Compared to what we did before when we ignored the effect of the live load. So that's that one. And the other one I want to show you is this one. Okay? This one has a triangular load. So what happens is that, okay, we're going to do the same, find our beam weight, which is pretty small, but we still have it. So we got that, right? And we're going to add the weight of the beam uniform here compared to the load that we were given, right, of 10.8 is a factor triangular load, right? And that's what I'm trying to show here, factor triangular load. So that's your 10.8, and then your uniform load here, which is pretty small, right? Okay, you find your reaction, so there is a reaction, but notice your plot. Your plot is no longer triangles, right? We're giving a bearing someplace, so there is a 12-inch bearing. So that means this is center to center. So we add 6 inches and 6 inches to the face, right? And then we have the D distance, right? So we do that. So in this case, you cannot use the proportions. You have to use your formulas for shear, okay? And so this is the formula for shear. You have to subtract, right? What are you going to subtract? I'm going to take my VU here. I'm going to subtract the uniform load, which is the 0.64. And then I'm going to subtract also the triangular load at the distance X, right? Which is this distance now. So that's what we're going to do. So that's our formula for our shear, okay? Based on the triangular load and the weight of the beam, okay? And when the X value equals 35.5, which would change to feet, right? The shear becomes 104.2. So then this is the shear that we're going to design at the distance D. Okay? And the rest is the same. You're going to have a V sub C component. You are going to have your phi V sub S, right? You know where the concrete limit is, but that limit is not where you stop. You stop putting stirrups at this value, right? Okay, so we do the same. After that is the same, okay? Find B sub C, find the limit, right? We got it bigger than that, so we need the stirrups. We need to find the length of stirrups. We cannot use proportions anymore. We have to use our formula for shear. And what we want is, we want the shear to be 25, and we want to know where that happens. And so we solve for X. Now it's a quadratic equation. See, that's the complication, right? So we got a value of 188 inches. So 188 inches needs to be covered from the center line, right? But if we go to the bearing face, is 182 from the face of the support, because remember 6 inches from the center of the bearing to the face of the bearing, right? So we need to cover from the face 182. What is my required value? The same as before. You do VU at D minus the phi V sub C. Remove the phi factor. We get that value, right? And then we check compared to the limits. We are below the 4. So that means D over 2 and 24, right? So far, we got a maximum spacing of 14, right? And so this value will be valid all the way to phi V sub C, right? Why? Because that value is right at phi V sub C. After you go below phi V sub C, you are here, right? But remember, always check this now, because in order to use the formulas, you have to satisfy minimum. We do not find the actual minimum area of the stirrups, but we indirectly find the spacing coming from the minimum requirements, okay? So you always have to check that minimum. All right, so here is the minimum requirements, just to make sure. 28 controls is greater than 14, so 14 is good then, okay? So we will use 14 as the maximum. Now the code requires that we check across, right? Across, you have to satisfy a value of 24 inches, but the width of the beam is already 14, so 2 legs will cover that distance. So we are good there, right? Oh, wait a minute. The beam is 16. I thought it was 14. Make sure. Yeah, 16. So the legs have to be spaced no more than 24, but this is 16, so definitely you satisfy that. Okay, so that is satisfied. Then what are we missing? We're missing, right? So we have done, I have done my check here for my maximum. I have checked my minimums, right? But I'm missing my required spacing, this one, right? So I need to check that one. All right, so let me check that one. Find my required spacing. I'm using number 4 stirrups. Okay, that gives me number 8, 9.8, right? And so This is 9.8. So 9.8, and that means I'm going to use 9 inches. Okay, so my required spacing is 9, my maximum is 14, my minimum is controlled by 28, right? Okay, so here is the 9, and now we're going to create a table. We're using the same equation, right? And we know our reaction, we know our loads, everything is here. So we got a table, right? And we are going to find these different values, okay? So I start at 9, and I can go to my maximum, which is 14, and I just pick some numbers, okay? You can do all of them, 11 and 13 if you want, okay? But I just pick some. And I say, well, when my spacing is 9, I put my S here, I find my that. I don't need this value because that is your D distance. You have to cover as a minimum your D distance, right? But right now what you want to know is where you can change, right? And so you're looking for the other values. So I do the 10. Normally I will not even do that one because I want to jump from 9 to either 12 or from 9 to 14, okay? That's where I want to do my jumps, right? So 9 and 10 is too close. There is no reason to do that. So 12 would be 40. We put it here, you get 44.3. Add your concrete, you get 94.3, right? And then what you do? The question is, where is the value of 94.3 in my graph? So you put 94.3 in your equation, solve for x, and then give you your value. Notice that the answer is in feet. You have to change it to inches, right? You can also find this value by doing the 103 here, right? In your equation, solve it, and you get that number. You do the same for the 14. So now we need to find 88. So where is 88 in my graph? I put it in the equation, solve for x, and there is my value as this distance. Okay, that just gives me an idea where I can switch. So I go 1 and 2 from the face, right? And then if I do, I want to switch to 12. So I need to go past 71. Okay, so I do 1 and 2, and then 8 and 9, that will be 72 plus 2, that's 74. Okay, 74 is greater than this. Now I can change to 12. So next I'm going to do 9 and 12, and that gives me 108 plus 74, that's 182. So that covers exactly my 182 I needed to cover, right? Then I'm going to add 2 additional ones to cover the remaining portion, right, at 14 inches. Right? And this value of 14 has to be less than the minimum, right? And the minimum is 28, so we're good. I just kept 14, okay? So I put that there. And that was added just for construction, and that finishes the problem. All right. Okay, so you have, lots of examples here that you want to look at. I can cover most of them. They all have little variations, so depending on what you need. I think we have done. Yeah. Okay. And so review that. There is homework too that you can look at in general. Okay. This one right here, notice that you have 4 legs. So you use 4 legs, right? This is wide. The beam is pretty wide. The reason for this example is because, as you can see here in your formula for, let me bring these design aids. In your formula for minimum, right, the B value is important. So if this value is pretty large, this S is going to be very small. And in minimum may be controlling the whole design, right? And so in this case, when you find minimum controls over all the other values. So now you have to use 11 inches. Okay? So you are no longer using your D/2, because minimum happens to control. That's the only difference in that problem. Okay? That you are controlled by minimum. So that's what I always said, check minimum, okay? Especially when your beams are pretty wide, you want to check minimum, okay? Because that may control your space. All right, so that's the end for this, and that will finish here, and we will start columns next.